So yes, I am Julian Doherty, and this is real-time strategy at light speed. So I'm a lead developer at Envato, which is a Melbourne, Australia-based company, and we provide online marketplaces for creatives who want to buy and sell digital assets. I think we're hiring as well, so if you're interested in moving to Australia and working, then come and have a chat. I also run the Elixir Melbourne meetup, and if you're in town ever, come along, drop in, maybe do a talk if you're interested. So let's talk about spaceships. Not that kind, and not that kind, not that kind either. We're looking for something more like this one, and like this one, and this, even more like this, and totally like this. And it's not going in reverse, if you're asking. I'm well qualified to talk about spaceships. I know a lot. I've played a bit of Kerbal Space Program, like quite a bit. I'm also, as we said, I live in Australia, but I'm from New Zealand originally, and we're one of the handful of countries that has space launch capabilities. That's the red and the orange ones. We're down there in the corner. Kind of pleased we got included because usually we get left off maps. So this is Rocket Lab. They're a New Zealand-based launch company, and they've picked up about 6% of global launches since they launched a couple of years ago. I can take some of the credit for that because I bought a pair of commemorative It's Business Time socks to celebrate their first launch, the commercial launch, which was named in honour of one of New Zealand's other great success stories, Flight of the Conchords. I currently live in Australia though, which has no space program to speak of. They did once launch a lipstick-shaped rocket for the UK. So I'm a big fan of hard sci-fi. So that's the subgenre where it tries to stay as close to reality as it can and as accurate as possible. So basically real science, but it's using more advanced tech. That mostly means plain old Newtonian physics. If you're going to go somewhere, you've got to push yourself. You're going to stop, you've got to push the other direction just as hard. And that's how rockets we have today work. So we have rockets that have really high thrust that can push you really hard, and we have engines with really high efficiency that can push you for a really long time. What we don't have is engines that can do both, so have high thrust and high efficiency. So one of the hand-wavy things that hard sci-fi does is solve that by having the concept of a torch ship, which is something with infeasibly good performance, where you can burn your engine at high thrust, like enough to crush your organs for months or weeks. So it's a plot device that lets you have a plausible setting where solar system's colonized. So Dread Empire's Fall series is a great example of that by Walter John Williams, TLDR, spaceships shooting each other. And the Expanse series of books and a show on Amazon Prime Video, and TLDR, lots of spaceships shooting at each other. So I think everyone here would have seen Erlang the movie, but what if we did Erlang the movie in space? It would go something like this. So the phone rings. Hello, Mike. Waiting. Still waiting. And like 45 minutes later, hello, Joe. So the reason for this is light. So light is fast. It can go around the Earth 7 times in a second. I would have gotten here from Melbourne a lot quicker if I could have. But not that fast. It takes like a second to go to the moon. And by the time you get to interplanetary space, it's really slow. 3 minutes to Mars, usually more like 20. So that delay adds a lot of suspense and drama, because if you're a ship in combat and something's, say, 10 light seconds away, you've got to anticipate what it's doing 10 seconds from now based on information that you can only see that happened 10 seconds ago. So you've got to be strategic around how you do that. So that could make a really cool game, which is what I started working on. So what I want to do is something 2D. I've got torch ships, got light signal delay, and potentially got thousands of players in there. Like no one's going to play my game, but whatever. I'm going to build it to do that. So if you worked in any kind of online product that's iterating and growing, you would have seen this. So the first 90% of features account for 90% of code, the next 90% account for 900%. So code starts out fresh and well-factored, but over the years, requirements get added, more things get added, and it gets clunky. So if we implemented this in an Elixir like this, so we've got an enemy ship, and it's got health, position, velocity, acceleration, target it's going for, and then we've got an update function that takes the state and iterates over those things and gives you an update. So this could be inside a gen server running in its own process. That would be a pretty common way of approaching this. Next, imagine you've got an asteroid code that looks something like this. So it's got name, size, it's got a set of fixed orbital parameters, so we can just, it's deterministic, we can calculate it more easily that way without doing full physics on it. And this is cool, like it's great at first, we've got a thing working. Then someone says, okay, why can't asteroids have feelings? And be able to move and have health and be smart enough to know when it's being targeted and get out of the way, and then decide it's annoyed with the planet and go and smash into it. And that was actually a plot line in the Expanse. So then one of the software devs says, well, asteroids, they only use the on-rails orbital mechanics. Can't do that. And the product guy's like, just ship it, do it. And so yeah, another if statement gets added to the monolith. So you've got to think about composability, how you do this. So how do you break it down into manageable chunks? You want to be able to look at something in small enough detail to be able to understand it, but at the same time, compose them into a big enough thing that you can run the whole system. And you want to do it in a way that you can actually add on to it and build as you go. So enter ECS, so this is Entity Component System. And in game development, this is a commonly used pattern for structuring logic in real time. If you need performance to update it, but you also want to be able to make changes to this and iterate on it as your project progresses. So at the top level, entities are just coarse-grained objects. So anything like spaceships, planets, torpedoes, space stations, sad asteroids, whatever. It's just an identifier, usually like a UUID or an integer. Maybe it's got some debug information, but that's it. Entities on their own are pretty useless, so you can add arbitrary components to them. So these are data values that can be composed to define what properties entities have. And they're totally flexible. So any component can be added to any entity. Entities don't have a type, they don't have a schema. The behavior is solely based on the components that they contain. So if we're going to have our sad asteroids, maybe it initially looks like this. So it's got a name, size, some orbital parameters there so we can calculate its position, and the position that gets updated every frame so we can render it. And then we can move it to something like this. So it's got a name, size, health, position, velocity. If you want to add components for movement and target tracking, sure, go for it. If you want it to be smart enough and not get rammed by a 2-mile-long spaceship, sure, add that too. And the nice thing is you can do this per entity. You don't have to be global. You don't have to alter all asteroids. You don't have to subclass anything. You can do it at runtime as well, so you can change the behavior on the fly. So that's cool. You can add features. You're not constrained by your initial design. Still don't have the logic. That's where systems come in. So systems are one logical thing that processes one thing. So they just care about some components and not one component on an entity, like all components for all entities of that type. So what the movement system could do is it just updates movement. And the sad feeling might do other things, but it might update movement too. So our movement system could look something like this. So you've got a system state which contains all the components and all the entities. And when it runs, for each entity, we grab the position, velocity, acceleration, do some basic physics, and update the state for the whole system. So this is just movement. Don't have to deal with AI or collision detection or input or anything else. There's nothing coupled in here that's actually making it harder to reason about what this bit of code is doing. It's just in that one thing. So the data doesn't have to live together. That's the nice thing about it, is that you don't have to run this per game object. So it's not an actor or a struct, or if it's OO, it might be an object. But it's across all instances of that type of component, within some context, like a single game. So it's sort of like a column database table. So the components can live wherever you want. And you get some nice benefits from this. One of the ones is performance. So it means instead of having to pass around a whole huge entity, which might have dozens or hundreds of fields potentially, you just pass down components if you're sending messages across the place. If you're working like a low-level language like C, that gives you a cache-friendly way of accessing memory. In Elixir, we're kind of not quite at that level, but we definitely get the benefits from having smaller bits of data to pass around. So that means no shared state processes message passing. So if we wanted to have like a concurrent movement system, we get something like this. It's kind of a wall of text. So we'll break that down a little bit. So it's a gen server. When we kick it off, we've got an event bus that we subscribe to, but it's like a hand-rolled thing. So we've actually got a set of component types that we tell the event bus about when we subscribe to it. So we only get those events for those components. And then we set up like a process, send after to do like an update every once a second. And then we build our initial state and kick it off. So the event bus can be backed by Kafka or whatever else. It's just hand-rolled in this case. It's just like another gen server. So if you want to send a message to ourselves to do the update, it just does whatever it does to move the state to the next step, and then it triggers the do update again after a second. And then we kind of get to the bit where it's dealing with actual ECS events. So I've got a handle info that pulls in like a number of events, like a list of events, and it'll call handle ECS event for each one. So we've got a put entity and a put component. They run through. And this ends up looking sort of suspiciously like GenStage we were hearing about before. And this could definitely be implemented with GenStage as well. So on each event, we update our local state, replicate what's going on out in the world, which is cool, but we need to talk about the light speed bit. So we just want to think about what is time. The Uber driver we had last night had some good ideas about time. I think the gist of it is that the past or the present don't exist, only the future. No, hang on, only the present or the past. But tarot readers, they can sense your aura, and they can use your aura to tell the future, which doesn't actually exist, but it does. But they're just doing it for the money, and they should use their talents for the good of humanity. Dude still charges like $40 for driving across town, so maybe not for the good of humanity, but that's cool. He had like a cute white dog, so he was cool. So say we've got two spaceships. So one's Joe in space, one's Mike in space. And one of them sends a message, and that goes across at the speed of light, and it reaches the other one, and they've observed it occurring. Now my 6-year-old came out the other day with, time has to exist, otherwise everything would happen all at once, which is, he's big on science videos on YouTube. That's pretty much it. It's just another dimension that you've got to put events in. So if you imagine our one-dimensional universe there, and you add time as an extra dimension, and we've got Joe and Mike sitting there in their spaceships, we get a space-time diagram like this. When Joe sends a message, it creates a light cone like that. And what that light cone means is that everything on the edge of that triangle, that's what will see the event from Joe. Everything inside has already seen it. Everything outside will never see it, at least not at that point in time. It might later. So the event goes outwards at the speed of light. Mike and Joe are not moving in space, but they're moving in time. Then eventually, Mike gets to the point on the space-time cone where he meets it and he gets the message. So you can look at this on the flip side as well, where if we look at the point of Mike going backwards in time, we get a light cone going backwards. And you can kind of use this to query what has happened in the past in space-time. So in this case here, we've got past Joe sending a message there. That's where it intersects the line. So we can tell that Mike will see that message at that point in space-time. So for any point, you've got two light cones. One for events going forward in time that you're like projecting, and another one of events that have happened in your past that you can see. So in 1D space with time, that's a triangle. In 2D space with time, that is a light cone in 3D. So if you wanted to imagine this in 3D, it's like a light goes on and then a ball goes out at the speed of light, but you can't visualize 4D things, so yeah. So that's kind of the basis of how we can model this. But these are just like systems you could build in ECS. So say we wanted to build one that actually bases on that future light cone. So let's call it the future propagation system. And what it does, it's going to track the entities that can observe things, that's Mike, and the position of things that can emit events, so Joe. And it spawns a task whenever an event happens that goes outwards at the speed of light. And the task starts at the event origin and then expands outwards. And then each iteration, it'll go and check to see, okay, who can see this event right now? And then send a message to them to say, hey, this happened. And then you do that by passing them a component as well that they can consume. So the thing with that is like, how can we actually efficiently track all the entities in space that could observe an event, even when those events are moving around as well? So you can use a thing called a quad tree. So a quad tree is a data structure that's used a lot in gaming and geospatial things. It's good for collision detection and figuring out what is near what else. So everything in the world is put into a big bounding box. You split it 4 ways, so down the middle that way, down the middle that way. Then you recursively do that smaller and smaller until you have got everything in its own box. And it means that you can like logarithmically query and to see what you're intersecting with. So if we have our event, looks like that, goes out like a circle from a point. And we want to find all the things it intersects with. So is it in the global thing? Yes, it is. Split that into 4. Which of those is it in? It's in the 2 on the left. Then we'll split those into 4 again, and then recursively go down and down and down until we've got a list of events that we've either hit, or some, or none, or multiple. So the future light cone is, problem with that is like, how can you share that quadtree state across processes? So you'd have to implement it with ETS or something like that. So it's not going to be a persistent data structure in the process state. There's some yaks to shave there to make it concurrency free, like not have concurrency bugs. So I didn't go too far with that approach there. The other way of doing it is to, the thing is there are way more events than there are entities. So you're going to have a lot of processes spawned, I mean potentially millions. Processes are cheap in Elixir, but they're not free. If you've got millions of them, it's going to count for something at some point. And you've got to dynamically update this as things are moving around as well. Backing it with ETS is going to make it harder. So the other approach is to use the past light cone. That's when we're looking back in time to see what's happened. So past propagation system, it tracks time in the position of events that have happened. So Joe sending the message, hello Mike. It runs in a single process. Well, you could scale it, but this actually runs in a single one because it can be fast enough. In each other update, you've got to iterate through all the entities that can observe the past, so all the mics. Then you've got to find all the events that meet their past light cone, which is Joe sending hello Mike. And then you send a message to them by putting an event with a component for that thing. So one of the things with the past light cone is then how do you efficiently track and find all the events in 3D space over a period of time that an observer could see. So you've got to use an octree for this. So we had quadtree before, which is 2 dimensions. If you're going to go 1 dimension high, you get an octree, which has got 8 levels. So the way this works is you have a cube, split it into along each axis, so that way, and that way. So into 4, into 8. And you can implement this as a tree with a recursive structure like that. And the same deal, like every point is in there. So why in 3D when we've got a 2D game? Because we've got 1 dimension for time. So what's happening is you go up through this cube, each of those is a later and later time. So with the future light cone, we're actually using time as time. So we could do it in 2D, but for this one we need to encode time as a dimension. Tree structure is actually really a good fit for persistent data structures with immutable data, like we have in Elixir. Quad trees are too, it's just that it's not as good a fit for our requirements there. So for the past light cone though, we've actually got things that work better for it. So all the past events are immutable. Something's happened in the past, it never changes, like it's not spaceship whizzing around at the current date and time. So that's easier to build. It also means events are only added, so it's append only. So we're never deleting things. And it means we can actually keep that all in one process because it's actually easier to build and it's fast enough to work that way. So I built one and you can put 10 million events in there and then you can do 100,000 entities querying that. That's like single threaded, that's not scaling it out with multiple processes. So which is good enough. Like probably the C and the Rust people are like, yeah, whatever. But for my mum said it was cool. The thing with the octree is how do we handle out of bounds growing? Because by nature, every single time we insert a new event, it's at later and later and later time. And usual octree implementations are like a fixed bounding box. So what we do is if an event is outside any of the bounds, we just double the bounds in that way to make it like double the size to fit the thing. And then we just pull all the data out and reinsert it again. So it's slow and naive, but it works. And over time, it's amortized over enough inserts, so it ends up okay. So you have a thing that looks like that. We get another event that's outside, so we just make it bigger and put everything back in there again. Next one is how do you deal with data growing? You've got an online thing that's potentially running for days or weeks or months. You're going to get a lot of data in there and you're going to run out of memory eventually. So the solution for that is pretty simple too. We just throw away the bottom 4. So our octree has got 4 on the top, 4 on the bottom, like that. And then we just add 4 more on top. Then we delete the 4 on the bottom, and then we've got our new thing. We've just discarded all those events on the bottom. They'll just get garbage collected automatically because we're not referencing them anymore. Because that going upwards is time, you just throw the bottom layer away. You've gotten rid of the oldest half of your data, which you want to do periodically. So how do we query events in the past with an octree? Basically got to get a cone and then see where that cone goes in. So Mike is at the top. Mike's going to project the cone backwards through the octree. So the top is now, going down is like points in space-time in the past. And then we find that there's a cube where Joe is in, and Joe is saying, hello, Mike. And that's how we can tell that Mike needs to know about this message. He's observing that now. So I've got a library to do this. It's a persistent octree data in pure Elixir. It's very, very rough, but it works, and it's kind of fast enough for my needs. And yeah, propagation, the game. And the development status is Half-Life 3. Yeah, it's still vaporware, sorry. I kind of wanted to have a demo to show off today, but yeah, life happens. The big pieces are all working, but I haven't got them together yet. But coming soon, so stay tuned. And follow me at madlab or juliandoherty.com to find out about it. Thank you.